Welcome to this explainer. Look, if you're an engineering student or really anyone trying to wrap their head around electrical networks, you know dealing with alternating current can feel a bit like, well, learning an entirely new language. But here's the secret. It really all comes down to mastering just a few fundamental mathematical operations. So today, we're going to crack that code. We're looking at a detailed guide on the mathematical operations of vectors. Let's just dive right into this.
So this image is straight out of a foundational textbook. And glancing at it, yeah, it looks incredibly dense, right? You've got formulas, subscripts, symbols packed totally tight together. But don't let it intimidate you. What we're actually going to do in this session is translate these dense equations into a really logical step-by-step visual toolbox. By the time we finish, you won't just be memorizing equations. No way. You'll know exactly which tool to pull out to solve those complex electrical problems with absolute confidence. Okay, here's our roadmap for today. First up, vector basics and setup. Second, adding and subtracting vectors. Third, multiplication in two forms. And finally, number 4, division using polar form. All right, section 1, vector basics and setup, laying the groundwork. You know, every great construction project needs a solid foundation, right? And here, that's our baseline vectors. We have two initial AC vectors presented in what's called rectangular form. We've got vector I1, which equals A1 plus JB1, and vector I2 equals A2 plus JB2. Now, what's really interesting here is how this actually splits the vector into two distinct personalities. The A part, that represents the real part of our vector, the standard numbers you're totally used to. But the JB represents the imaginary part, denoted by that little j. You have to handle them as distinct components. They live in the same equation, sure, but you can't just mash them together without following the proper mathematical rules. Moving on to section 2, adding and subtracting vectors, the rectangular method. Now this perfectly illustrates the absolute beauty of the rectangular form. Whether you're adding or subtracting, the logic is wonderfully simple. For addition, you literally just group the real parts together, so A1 plus A2, and then you group the imaginary parts together, giving you J times the sum of B1 plus B2. You're just combining like terms. It's like sorting apples and oranges. For subtraction, it works exactly the same way. Just match the sign to the operation. You subtract the real parts, A1 minus A2, and subtract the imaginary parts, B1 minus B2. It keeps your real components with your real components and your imaginary ones with the imaginary ones. It is incredibly clean. But getting those grouped numbers is really only half the battle, because in engineering, we often need to know the actual size and direction of that resulting vector. So how do we find that? Well, it's a quick 3-step process. Step 1 is exactly what we just did. Calculate your new real and imaginary groups. Step 2 is finding the magnitude, labeled IM. Notice that formula? It's the square root of your real group squared plus your imaginary group squared. Honestly, that's basically just the Pythagorean theorem. You're literally just finding the hypotenuse of a right triangle. And finally, step 3 is finding the phase, or the angle, denoted by theta. You take the inverse tangent of your imaginary group divided by your real group. By anchoring the textbook formulas to this repeatable 3-step process, you can easily extract real-world meaning out of the raw algebra. Let's hit section 3, multiplication in two forms, the narrative pivot. Okay, this is where we kind of have to completely rethink our strategy. If we try to multiply our vectors while keeping them in rectangular form, things get messy fast. You have to multiply every term by every other term, the classic algebraic expansion. You get A1 times A2 plus J times A1 times B2. It's just a lot to keep track of. But the absolutely crucial algebraic shift happening here is right in the middle. When you multiply the two imaginary parts together, you get J squared. And in complex numbers, J squared equals -1. That means that specific term suddenly flips its sign and transforms from an imaginary number straight back into a real number. It's mathematically fascinating, but let's be real. Doing this by hand for a massive circuit network is basically a recipe for a calculation error. Which naturally leads us to a question, one that pretty much every tired engineering student has asked at 2 a.m. Is there an easier way to multiply vectors? Like, is there a cheat code to just bypass this complicated, messy expansion? Well, I am thrilled to tell you that yes, there absolutely is. Behold the elegant solution, polar form. We just looked at the messy expansion of rectangular multiplication, right? But look at polar multiplication. If you first convert your vectors into polar form, meaning you just have a magnitude and a phase angle, the math becomes unbelievably simple. To multiply, you simply take magnitude 1 times magnitude 2, And for the phase, you literally just add theta 1 and theta 2 together. No FOIL method, no trying to remember J-squared rules. Just multiply the big numbers and add the angles. It is a massive, massive time saver.
All right, Section 4. Division using polar form, the ultimate cheat code.
Just think about trying to divide long, rectangular algebraic expressions for a second. It involves complex conjugates, massive unwieldy fractions. It's a nightmare. But look at the polar division formula. It follows the exact same sleek, intuitive logic as polar multiplication. To divide vector 1 by vector 2, you simply divide their magnitudes. IM1 divided by IM2. And the phase angle? You just take the top angle, theta 1, and subtract the bottom angle, theta 2. What used to take minutes now takes literally seconds.
So the absolute crucial point here is really understanding this beautiful pattern that the polar form gives us. I really want you to burn this comparison into your memory. When you're doing polar multiplication, you add the phase angles. When you're doing polar division, you subtract the phase angles. The magnitudes always do exactly what the operation says, multiply or divide, but the angles do the simpler math of adding or subtracting. Honestly, this is the secret to flying through AC circuit analysis.
Let's summarize this entire explainer with the ultimate cheat sheet. We've gone on a bit of a form transformation arc today. We started with rectangular form, and we found it was perfect for some things, but kinda terrible for others. This table breaks down your entire strategy. If your operation is addition or subtraction, the best mathematical form is rectangular. Just group your reals, group your imaginaries. Easy. But the second you need to perform multiplication or division, you should immediately convert those vectors into polar form. By shifting forms based on the operation, you're working smarter, not harder. You're actually using the math to your advantage instead of constantly fighting against it.
And there you have it. We took a dense, intimidating textbook page and turned it into an actionable, structured toolbox. Armed with these foundational vector tools, you literally never have to guess how to handle the math in an alternating current network again. You know exactly when to stay in rectangular form and exactly when to pivot to polar. So my question to leave you with today is this. Armed with this knowledge, which complex electrical circuit are you going to decode first? Thanks for joining me for this explainer, and happy calculating!